إدارة هذه الجلسة الأخيرة، مش الأخيرة، الأخيرة هذا اليوم طبعا. فهناك عندنا إن شاء الله 5 مداخلات، ورايح إن شاء الله نبدأ بال keynote speaker حول ال Artificial Intelligence Application in Hydrogeology and Groundwater Management. It will be done by Khalid El-Haj from the United Arab Emirates University. Exactly. So the floor is yours, and you can. I have to give first the bio. I am sorry. I am sorry.
Yeah.
I am sorry.
I can say the bio.
You can read it.
Yeah, he's my student.
Ah, okay. It's better that you give it.
So, without even reading his bio, I've been working with Khalid since 2019. He got his PhD just a few days ago on Thursday, 25th of April, with an excellent evaluation. He specialized in artificial intelligence and groundwater. He built his own library, which is called GEOS, and it's open access library. He made a very good validation and optimization of his own models. He published already some papers in conferences and also on Scopus, and he submitted 2 papers which will be published soon, inshallah. He's one of the most intelligent and smart people that I have ever met, to be honest.
Thank you very much.
So Khalid, you have 20 minutes, please. You have 20 minutes
Okay.
for your presentation. So thank you. You can start, and the floor is yours.
Okay. Pleasure to be in your presence. My presentation would have a different structure compared to the previous ones. I will not be going through one project basically and covering the methodology and results and etc. Instead, I would go through several projects very briefly to do two objects mainly. The first is to shed light on the progress of AI in terms of hydrology fields. And the second is to elicit discussion and collaboration from the audience. Okay. So these are the projects I will be discussing, and there will be a brief introduction and conclusion. Since most of you are hydrologists or hydrology related, you already know the importance of groundwater. It covers the primary need of more than 2 billion people, and it's used for half the water used for the world food supply, to irrigate the world food supply. And for the GCC countries, it's one of the most important resources. So it's imperative that we manage and regulate this important resource. And managing this resource involves many aspects, including the regulation, the monitoring, the optimization, the prediction, and in addition to aquifer delineation. And for the aquifer delineation, we needed to do it because it's one of the major steps that we need to prevent pollution, to prepare for the disasters, and to optimize the land utilization. And this is the first project that we did. We published it as a book chapter in Scopus indexed library. It's called Model Prediction of Groundwater Level Fluctuation using Geoinformatics and Artificial Neural Networks. Most of our projects, of course, due to biasness, are based in Al Ain City. And in this project, we basically looked at the groundwater fluctuation data for around 54 wells. And out of these 54, we chose around 7 wells. And these 7 wells were used to train an artificial neural network to predict the fluctuation in the groundwater. And the artificial neural network had 5 inputs: the rainfall, the humidity, the evaporation, the temperature, the date, and the location, the latitude and longitude. And based on all of these 5 inputs, it would predict the groundwater level at that location in certain time. The model was built using Python and we utilized the PyTorch framework, and we used a high-level API called FastAI to avoid the flexibility and complexity of the PyTorch framework. All of this was run locally on our machines in the lab, and we used Jupyter Notebook and VS Code to write the actual code. For the second project, this project was submitted and accepted to the COP28 initiative, the comprehensive report, and hopefully it will be published soon. We tried to predict the groundwater salinity using meteorological data. And one point I would like to note here is the location of the samples. If you notice, they are basically shaped like a plus or a cross sign. There is a lot of samples on the horizontal and on the vertical sides. This is mostly due to following the farms that are on the major road intersections. On your right side, you can see the Hajar Mountain, which is basically the dividend between UAE and Oman. This would come in later on. So basically, we created a random forest machine learning model, and we fed it 6 parameters: the easting and northing for location, the date is encoded into ordinal value, the rainfall, evaporation, and temperature, and it would predict the TDS. This is our observation versus the prediction. The blue is the prediction, and the yellow is the observation. The observation is very hectic. However, if we smooth it using time series methods, it would actually be very closely related to the observation, to the predicted values. One thing to note, the model accuracy was within acceptable range, and we analyzed the trained model to find which factors affected the salinity of the groundwater. And interestingly, the highest affecting factor was the easting parameter. So basically the horizontal movement of the well from the Hajar Mountain. And this indicated a very interesting fact that the water would increase in salinity the further we move from the recharge zone, which is the Hajar group. Second is the date, which indicate the seasonality of the rainfall and water. And the northing, which move exactly along the recharge zone, but with a slight deviation to the left, was also very significant. The temperature and rainfall and evaporation were of little effect on the prediction of the salinity. The third project is still under review. We are using machine learning methods to extract insights from hydrogeochemical data sets. We studied 3 locations in UAE. The first is Al Ain City, as usual, near Hafid region. The second is in Fujairah, and the third is in Ras Al Khaimah. We collected 45 samples, and we analyzed all of these samples, hydrogeochemical features, and basically the signature of each sample. We used a machine learning model to impute any missing values, and we tested many models, and we found the most optimum one was random forest. By the way, different models performed differently for different elements. For the chloride, for example, the model that performed best was random forest. However, for the sulfate, the model that performed best was the K nearest neighbor. So different models were used to impute missing different elements. Next, we wanted to choose the most optimum number of clusters that represent the actual data. So we used the silhouette score method to determine the most optimum number of clusters. And then we chose, we had the highest 4 scores were 2 clusters, 5 clusters, 4 clusters, and 3 clusters. The 2 clusters were problematic due to several reasons, and I will be afraid to discuss it due to times. But the most reasonable one was 3 due to the geographical distribution of the 3 regions. The 4 and 5 were problematic, but we wanted to check. Including in the data that we collected were 2 samples, which we collected as a test from surface water in Mubazzara Lake. And the model actually distributed these samples into a different cluster when we asked it to make 4 clusters of the data. And this was the most accurate. For the 5 cluster, it was oversensitive. And you can see actually in the lines that the purple dotted line and the blue line are almost overlapping in all of the elements except for the radon readings, which we considered as an oversensitivity in the model detection, and we stated set on the 4 clusters. So the conclusions that we got from this project: first, the Fujairah location. The Fujairah was one homogeneous cluster. No matter how much we divided the data, the Fujairah was still the same cluster. And this indicated that there is an extremely high homogeneity between the samples in collected in Fujairah region. And this is a certain indicator that this is one aquifer. Another interesting fact was in Ras Al Khaimah, 5 of the samples, of the 25 samples collected in Ras Al Khaimah, were classified as part of Al Fujairah. And this indicated either a deep aquifer that is shared between the 2 locations, or some similarity in geological formation that allowed the water to give a similar signature to the samples in Fujairah. And finally, the 2 samples that we used as test, the model was able to actually classify them into their own cluster. Finally, the last project I will be discussing in this presentation is advancing groundwater management, a novel machine learning approach to aquifer delineation. And this project was the majority of my PhD. Basically, we studied 2 data sets. One is from the state of Texas in the US. It contained 1.6 million readings. And you can see the actual aquifers. It contains 9 major aquifers. Each profile is colored based on the aquifer it belongs to. And the second one is a synthetic data that we created with extreme chaos to increase the complexity and the difficulty on the model to predict the actual aquifers. This is the spatial distribution of the samples across the 9 major aquifers. On the left, the A figure is the natural aquifer, the real data set, and on the right is the synthetic data set. And you can see that it's actually well distributed compared to the real one. For the methodology, our model actually is divided into 3 major parts: the framework, and the optimization, and the visualization. The framework is composed of 2 stages: the pre-processing, where we clean the data, we fill the missing values, etc., and the clustering model. The clustering model is where we had the majority of the novelty in the research in it. I will not be discussing it in detail due to the time restriction, as well as the paper still under review. And the parameters would allow the model to have the flexibility we need to achieve the highest accuracy. After creating all of this, we inserted all of it into an objective function to run the optimization algorithm. And the objective function would produce adjusted random index, which would be at a certain degree of accuracy. And finally, at the end of the optimization algorithm, we produced a recommended set of parameters that we used to draw the output of the clustering algorithm into the spatial geographical map. And this map was actually created using the GEOS library that we developed for this project specifically. And finally, this is one of the interesting events. As you can see in the top left, the A figure is an actual real data set from the Texas. It contains 12 profiles for different wells, and these 12 profiles, or 12 wells, are distributed across 3 major aquifers. And using your eyes, it would be extremely hard to differentiate the 3 different aquifers based on these profiles. However, the model that we developed have successfully, with 100% accuracy, classified them into 3 different aquifers. And you can see the 3 different aquifers in the 3 figures remaining, B, C, and D. And this is the synthetic data set that we created. This is the state of Texas in 3D model, a bit fancy. And this is after we clustered them, each into its own aquifer. And this is after drawing it using the methodology that we created in the library called GEOS. This is a 2D look. On the right side, the B figure is the actual field, and on the left side is the model prediction of the aquifer boundaries. Finally, for the recommendation and conclusion, artificial intelligence in hydrology is not very well utilized from what I have seen. And the expertise that try to utilize it is almost all new. The experts do not really have the interest, or shown the interest in the research at least, to start using it. The second and most important recommendation I would like to propose is the data. Data is the new oil, yet we are suffering extremely from the lack of data. And for my model, I went to the US to get the data to train the model because in the GCC there was not enough data to train it. So collaboration and data availability are one of the essential steps that we need to be able to utilize AI in hydrology in the GCC. And there have been initiatives similar to the G20 data gap initiative that Dr. Dalal mentioned. And these initiatives would start by identifying the gaps, then identifying the steps needed to fill in the gaps, and finally start filling the gaps. I think that there is a need for a general platform that would allow for the users to basically share their data, because the data exists, but it's fragmented in many different locations that you have to look and contact people to collect it. And with that, I end my talk with thanking the Gulf Water Science and Technology Association for their kind invitation, as well as KAHRAMAA, the UAE, the Geoscience Department, the Water and Energy Center, as well as the UAE for University for providing the HPC for calculations. And finally, I would like to extend my thanks and heartfelt appreciation to my main collaborator and PhD supervisor, Dr. Dalal. Thank you very much.
Thank you very much, Khalid, for this excellent. Well, you have tackled several aspects of the application of the EI in groundwater and hydrogeology, so, and in different regions. This is very, very, very important, and the recommendations are very, very good. I like what you have suggested, especially for the Gulf countries, and to share and to collaborate. This is very, very important. So I have some comments, but we will leave it at the end about the results that you got. So now we will skip to the second presentation, which will be done by Dr. Abdelaziz, and it will be on mainstreaming the outcome of the UN Groundwater Summit within the Arab Strategy for Water Security from UNESCO. So I think the bio, you can give the bio. So you are very well known, but it's better that we have to.
If you can share the bio of Bishri if available.
Yes, yes.
Because Bishri was supposed to make this presentation,
but you can give what? So
okay.
Just 30 seconds for your bio. It's better because some people probably don't know you very well. Yeah. Okay. So.
Okay, please go ahead.
So I can give it because I know you very well. So Dr. Abdelaziz is an expert who is working in the UNESCO at Cairo office. He really made a lot of effort in order to advance water resources, and we have done with him several several projects and also several training. He is an active expert at UNESCO in Cairo. So thank you.
Thank you, Abdeladir. First of all, I would like to convey the apology of my colleague, Bishr Imam. He is the regional hydrologist in UNESCO Cairo office. He is in another mission in Baghdad, and he was supposed to have this presentation online. However, due to some unexpected circumstances, he cannot do it today. I will try to tell you a story of cooperation that we started since May 22, cooperation that involved many UN agencies, sister agencies, ESCWA, FAO, ACSAD, universities, Arab Gulf University, Mohammed Al Khamis, Muscat University, all of those regional partners, and the Arab Water Council for sure were major partners, major actors in this collaboration. The presentation Bishr prepared tried to cover all of these points. However, I will try to go through. The idea is in 2022, it was decided that a UN Groundwater Summit will be organized in the UNESCO premises in Paris. So it was a sort of preparatory phase from the Arab region to prepare or to try to reflect the Arab region challenges, the Arab region requirements in terms of groundwater. To some extent, yes, groundwater is very important here in in GCC. However, to some extent, in other parts of the world, or even in the Arab region, is not that important resources. However, so we started this cooperation with our colleagues in ESCWA and the Arab Gulf University and ACSAD and the League of Arab States to start a sort of consultation or dialogue what the Arab region wants to reflect in the UN Groundwater Summit. Major items covered improving knowledge for sure and information, more monitoring systems, strengthening the management of groundwater, especially the non-renewable groundwater resource, which is the major water resource here in the Gulf and even in many other areas in the Arab region. Conducting for scientific studies and cooperation over the transboundary aquifers. These 5 main issues that was reflected from the first consultation we had with ESCWA. There's another level of consultation were done during the COP27 where FAO, RNE, and League of Arab States, the coordination Secretariat of the Arab Ministerial Council of Water were involved, where other layer of requirements or challenges of the Arab region were highlighted. Something like legal and regulatory frameworks. In many countries, in Arab countries, there are many water laws. However, groundwater was not that visible item in these laws. Governance and its challenges, its problems with the implementation and institutional capacities and socio-economic considerations, and the use of groundwater in agriculture and how to link it, how it is linked to the livelihood of rural communities, and the complexity of all of this application or use of groundwater in agriculture sector. Based on these 2 levels of consultations, the whole UN agencies went to the Arab Ministerial Council on Water, and we got the approval of the major recommendations from the these consultations, and the Arab Ministerial Council on Water is the highest intergovernmental body in relation to water resources management in the Arab region. And we are an intergovernmental program, so it is a very important body for us, and I believe the same for all the UN agencies. So the main resolutions focused on reporting back to them on the UN Groundwater Summit, putting action plan for how to integrate groundwater in the Arab water security strategy. The UN Water Summit on Groundwater was held in UNESCO Paris premises. It was a huge event, more than 3,500 attendance online, 800 attendance in person, representing 139 countries, 18 ministers, 2,046 speakers, and more than 42% of these speakers were groundwater experts. The main document produced from the summit is the call for action, where the summit asked the countries to give more support, especially the financial support for management of groundwater, sustainable groundwater management, give more support and for sure financial and for monitoring, collecting data, quality data, strengthening capacity building at the human resources and the institutional levels, and trying to enhance or to use better the innovations in the area of groundwater management, and for sure strengthening groundwater governance. This is the main messages came from the summit through the UN call for action. At least from our point of view, one of the best outputs or fruits from this groundwater summit, that the summit brought groundwater on the agenda of the highest political level internationally and regionally and nationally as well. The summit also highlighted the importance of more responsible, sustainable, and protection of this invisible resource. And also supported highly the request for more cooperation over the shared groundwater resources. The report of the Council covered 7 themes, mainly data information, capacity development, innovation, finance, governance, groundwater in Africa. Africa is a global priority in UNESCO, and strengthening the science policy interface. Based on this summit, UNESCO, Cairo, and other UN agencies, FAO, ESCWA, and the Arabian Gulf University, we had many meetings and consultations that end at the end with the Arab Regional Groundwater Expert Group, which we tried to focus how to integrate, how to put groundwater sustainable management in the framework of the Arab water security strategy. Unfortunately, this strategy, the Arab water security strategy, did not cover fully the groundwater. And this, from the output of this expert group meeting, we were able to put groundwater on the radar of the on the mainframe of the Arab water security strategy. The meeting was attended by representation of FAO, ESCWA, هيئة البيئة أبو ظبي Environment Agency, ACSAD, UNESCO, Arab Water Council, League of Arab States, Mohammed Al-Khamis University, Muscat, Sultan Qaboos University, and all of those experts tried to put a plan how to integrate groundwater in the and how to mainstream groundwater sustainable management in the Arab water security. They tried the output in a number of axes. The first one focused on governance, working on enhancing the enabling environment for effective groundwater governance in the Arab countries, with a focus on the necessary legalization, the integrated and participatory planning for sustainable groundwater management, community participation, and promoting interaction between science policy and the practices of groundwater. For sure, as we mentioned in the previous session, yes, the science community has their own knowledge. However, in this meeting, we stress also the policy makers and the operational management have their own practical experience, which should be used by the science community to improve our science and its applications. The second axis of recommendation is focused on the data, information, the monitoring, and how to develop and manage information system related to groundwater, and how to make it accessible through updating hydrogeological maps of the promising areas. Other axes like financing, allocating and enhancing, and necessity to achieve sustainable groundwater management, the interface between science policy and groundwater practices, and the climate change, and how climate change is affecting the groundwater management in the region. One of the major axes that we were successful to include is cooperation among the shared aquifers, and this was one of the fruits of our cooperation with the Suez Development Cooperation. They are through our colleagues in headquarters in Paris. They are providing support to groundwater, transboundary groundwater management in the Arab region and in other regions in the world. And through this cooperation between UNESCO and the Suez Development Cooperation, we were able at least to put a vision on how to integrate shared water management, shared groundwater management in the Arab water security strategy. All of this reporting went back to the Arab Ministerial Water Council in Riyadh last year in November, where we got approval from the Ministerial Council, and with a recommendation or a resolution to produce 3 policy briefs on management of non-renewable groundwater, managed groundwater recharge, and strategies to protect the groundwater and the ecosystem dependent on it. I believe this is the first step towards promoting groundwater management, sustainable management in the Arab region. Thank you very much, and again, I would like to convey Bish apology for not being here, and I hope I tried to convey his views about this cooperation. Thank you very much.
Thank you, Dr. Abdelaziz, for this excellent presentation on the activities and the outcomes of the UN Groundwater Summit and its mainstreaming with the Arab strategy for water security. Of course, we will have the time to discuss because there are various activities that we can go into details, especially for the expert meetings that we had, and we have different action to make in order to promote groundwater management. So now we will skip to the next presentation, which will be done by Dr. Ali Maktoumi,
Yeah.
and it will be on feasibility and site investigation study for the aquifer storage and recovery application for water supply in arid area in Oman. Thank you, and you have, please, you can.
Yes,
You can
Doctor.
read, he's by you.
Yes, Doctor. Thank you, Doctor. Dr. Ali Khamis Al-Maktoumi is an associate professor in the Water Resources Management and the director of the Water Research Center in Sultan Qaboos University in Sultanate of Oman. He obtained his PhD from Australia in Environmental Engineering, Queensland University in 2007. He has led strategic consultancy and research projects in multi-topics, and he published more than 70 refereed papers, and he edited 2 books, and inshallah towards more successful.
Thank you very much. It gives me always a privilege to stand in front of you and talk especially about groundwater resources. It touches my heart always. And just connecting my talk to the previous presentation where the Arabian, or the Arab Council selected or shortlisted the managed aquifer recharge as one of the priority areas. So it's also a privilege for me to stand in behalf of the whole team to present a small portion of a project has been conducted in Oman, and it was sponsored and supported by NAMA Water Services, and led by consultancy team ASD for engineering and engineering consultant, and Consul-Aqua Hamburg and Acacia Water. So the whole idea is about conducting a real visibility work for site investigation study for artificial aquifer storage and recovery and applications for water supply in arid areas. I will skip this part. So the ASR has been recognized recently as an important thing, and I don't want to keep saying that. So ASR system is no doubt is one of the strategic options for the Gulf countries, where we need to bank or store. I always want to bank because this is really banking because it has a financial dimension. So storing water hydrologically during excess time or during low peak time, low peak demand, I would say, where we have excess water. So that excess water, instead of wasting it, and we have to harvest it along with whenever we have excess water to store it in the aquifer. So why we need to do that? Because of the episodic problems with seawater, where it's the source of desalination, where harmful algae blooms, oil spills, and extreme weather events where it's interrupt the desalination and the supply. And we experienced in Oman that going back to the aquifer system is a solution, especially during emergency and also during normal operation system where there is a peak demand. So this will enhance definitely drinking water supply security, and to some extent also will reduce the energy cost. And here you can see in the image, this is illustration where unfortunately the pointer is not working, but we can see easily the concept is just storing the water into the aquifer, and this aquifer has to be selected properly, studied very well, because we are injecting for the sake of recovering the water. So the project in Oman, it was based on a pre-visibility work where a number of sites has been selected. So 4 sites was a candidate for ASR, where we have to do a detailed investigation, and 4 potential sites has been studied, and for hydrogeological analysis, hydraulic analysis, transportation system, well field design for potential ASR sites. So in the map here, we are indicating, but the one circled with the red circle here is the one which I will highlight and present because it has a very nice take-home messages that I would like to pass through today. Okay, so the whole project is, the overall project objectives was a geological and hydrological study. Then we have to move for numerical groundwater model. And then for the whole 4 sites, then we have to do a hydraulic model after we feed it from the numerical model. Then we have to go for the infrastructure design, cost and estimation. Then we have to go for the economical model and then a final design and final cost estimation and tender documentations. But today I will focus on the one highlighted with the red, and also the text here, Al-Khawd site. And the goal for the modeling part was definitely to test the suitability of the selected aquifer, as you will see later on, and to analyze the operational scenarios, to optimize well field design implementing ASR system, and to predict the hydrochemical and hydraulic impacts of the ASR operation, and to provide inputs for the other models that need to be done all the way to the final design. The groundwater model I'm emphasizing here, it provides an insight in the amount of fresh water percent of the available surplus. We don't have to invent how much we can inject. It's basically based on how much available water during the low peak demand. And then we have to calculate how much water we can recover, because investing money in this, we need to put it in the ground and we have to maximize or optimize, I would say, the recovery. All right, so I know the time is limited, but I will try to just to give the cream of it. This is the ASR operational scenarios. It might be different operational scenarios for other projects in other countries or even in Oman. So the first thing you need to keep in mind that the design horizon for the groundwater modeling and ASR is 2045. So we included all the predictions of expansion in desalination and the demand and all the infrastructures for the 2045. And we linked that to 2 main scenarios. Emergency scenario, where we have to stress to go back to our aquifer system and stress it for supply during emergency situation. And through a lot of discussions, there is no time to discuss it, we came up with 13 weeks of injection, and this is very clear because this is the time where we have surplus of water during winter time. And then we have, usually we expect it to have like 6 weeks of rest or storage, leave it there, we stop injection, and then suddenly we have an emergency situation, we have to recover it over 6 weeks times. And then we have to see the response of the aquifer. Definitely there is an endless scenarios that you can address, but we have selected this one to test the visibility at this stage. Another scenario, there is no emergency, but there is a normal operation where we have to supply water. We have excess during one time, we have to inject it, we store it there, and then when we reach the high peak time, we have to go back and recover the water. So those are 2 scenarios that have to be studied well in depth. And those are based on those also, the other criteria is the available amount of water, and as you can see in those tables, based on those selected sites, we are showing the surplus water, which is on excess of what is used, which we don't produce excess, but this is during the low peak time. So for the 4 sites and associated with the nearby desalination stations, so we have all the data from our client, and also the ASR locations also available. The area is limiting factor, as you will see. We cannot just use the whole Doha, for example, to plan our injection system. So you have only available area, and you have to test how the system will act, and the water mounding or depression will develop when you have a limited area, because that area of the ASR must be restricted and protected, because it becomes like a well-filled area, and we don't want to interference with it. All right, so this is the site, and here I would like to just quickly highlight the constraints for the sustainable ASR systems we are having here. It should be located within this red zone, because this is the protected for the well field, and during the injection phase of the ASR, the groundwater level should not get closer below 5 meters from the surface, because it will induce geotechnical problems also to the infrastructure, because this is an urbanized area. During the abstraction phase, recovery, we have also to consider that the water table should not drop more than half of the saturated aquifer thickness, not to induce a severe depression, so then we cannot invite the seawater intrusion, which is also in the nearby area, and also it has to be 5 meters above the top of the well screen for the operation purposes. Okay, so let me give you an quick overview. What is the site here? You can see this is the blue site. Here is the well field, okay? And what you see the structure upstream is the recharge dam. Okay, so this is the recharge dam. In the past, we thought this is the area will feed, so we need to harvest water and allow more infiltration, so then we sustain the water supply. However, it turns, as you will see later on, that this might not go very well with the ASR system later on. Okay, so this is the also the public water supply. There are 70 public wells here, and we found out that we might need more wells for injection. And there are some private wells around, and this might have inducing some challenges later on for operating the ASR system. Okay, so the project started with a very thorough review of the already existing literature and data from the ministries and other water utilities. And also we have done some geophysical studies. We have followed with drilling projects and drilling coring, and also we have done observation wells and production wells later on. So, and those are very important. We have conducted also our pumping test to characterize the aquifer parameters, which are a very important input for our simulations and other models. So we end up of having all the parameters we needed to as an input for our model. This is a very important slide that I would like to bring the attention to. Look, we are having in the left side, I am having a couple in the top two, and the one to the left here is for 2021. So in January, I guess, for a couple of days in October, and you can see the shift on the gradient without any ASR. This is just a normal revision of the hydraulic head, the equipotential lines. And this will give you an insight how complicated is the site hydrologically. Why? Because in the beginning, the gradient is to the sea. It's just north. You see the red arrow here. Then later on here in the same year, just a couple of months, we are seeing that the site where we would like to have an ASR is receiving water from both sides. So there is a depression there. And then in another time of the year, there is a strong gradient toward the sea, stronger gradient. Then we are seeing, comparing 2018, and we are trying to see what we see. We see there is, to the west, the top images there. And then in the same year, for the same location, to the right. So what is happening when the water table over there? The aquifer is swinging its direction. There is something going on around the boundary of the ASR system. Makes it very difficult to estimate the gradient direction and even the value of the gradients. And this is crucial for the ASR system. And this is, you can see the gradient here in the bottom right side. You can see how the gradient is shifting north-northeast and south-southwest. And this is really create a very challenging situation for us as a team. The hydrogeological studies, the geophysical studies, all of those geophysical work, identifying the saline intrusion layers, and all of these helped us to conceptualize the aquifer system that we would like to simulate that will help us for further design. And this is the ultimate outcome of our design for the conceptual, and these are the drilling work and that identify the layers. So I don't want to go through the details of all of these things, but eventually we designed the ASR system to bring it to a real test, and those are the criteria based on the previously highlighted. So we are having an area of a limited area, in fact, here, because if you have seen, this is located in an urbanized area close to where SQU, and there is a land value, and many people want to invest the land, and they don't view water. It's not their business. But we realized that the actual protected zone has been invaded by different constructions and big projects, making limited area for the ASR. Now we have to live with that. Now this is what we have available, and we need to test the visibility of ASR. And there are others where we translated these, the depth of the aquifers, where we have to place our screens of the wells, the recovery wells, all of these technical things, I will just leave them. But those are the design criteria that we use for this particular site. This is the layout of the wells, 3 wells, because we found out that for the surplus water, the volume that we have to target, we need about 90 wells, considering the hydrological features and all the stuff. And so we have all of these, layouts and injection rate, recovery rate, etc. I don't know how to switch off this. Anyway, there's an animation here, but I can skip. And I go for the summary here. Here, the message here that there is a recharge dam. There are some rainfall events. The dam might become full once or twice or 3 times a year. That means there is a bolus of water injected into the aquifers, creating a high gradient. During this time, if we also inject water to the ground, what will happen to the injected bubble? It will be drifted away outside the recovery zone. But during low gradient, there is no water in the dam, there is no recharge events. The site is a very good candidate for hosting the injected water, which will remain, and we have simulated this for 53 weeks as we planned in the operation scenarios. So then we can recover almost all the water, and we use the chloride concentration as per the Oman standard for drinking water to trace it. And you can see easily here, after the rest, this is after injection, which is infiltration, the bubble increased, and then still after recovery, 52 weeks of recovery, still you see the bubble is within the recoverable zone. However, in the high gradient, the water, by the end of the rest, before we start even the recovery, the injected bubble already left the recoverable zone, clearly stating that you cannot do the ASR system while you still have a potential of natural recharge here in the site. This is here we highlighted also quickly. I'm highlighting here the infected areas during injection and during abstraction, because this is a residential area, so we have get a better insight of how much water, what is the influence zone, the radius, and what it was extended in almost like 8.5 to 9 kilometers without inducing significant damages. It is within our design criteria. Okay, so Abdul Qadir behind me. So I will skip this part, but here also, sorry, I have to highlight this quickly. We represented by a single well, multiple wells, because ASR, it will not be by a single well show. It will be by a multiple well that they have to act injection, and a big mound will develop, and then heavy abstraction, and that will create also depression. So we have studied many scenarios. The time is not enough here, and we have seen that by the time you inject in the upstream, when you start to recover it, then already the bubble left the recoverable zone of the downstream well. Okay, so this is also showing that this is the dot line. I hope that you can see it. The dot blue line is indicating the quality grade, the limit that during which under the low gradient everything is nice. We can recover almost all the amount of water that we are injecting. But in the high gradient, because of swifting and drift of the injected water, when we start to recover, during recovery, we start to invite sea. And the saline, what is the source of saline water? We are having an intrusion. It's a thin layer underneath, creeping the tank, intruding into the aquifer longer distance, regardless of the saturated thickness we have, and also the saline boundary. So when we stress the aquifer, keeping in mind that we were injecting, but the water is drifted, then we start to invite salinity, and then the quality of water recovered is passing the criteria, and this makes chemically, or from the water quality point of view, the ASR is not visible in this site. So basically, the take-home message, I will just not read the slides. The take-home message here is that this site, in fact, is technically is very suitable for ASR. Hydrologically is very suitable for ASR. It's in the center where we need the water, in fact. Densely populated cities in Muscat. The main lines that will get in the water for injection and taking back the water for recovery for the network is there. There's not a lot of investment cost here. However, what is happening of this swinging of the directions of water because of the private wells operating around the site, it doesn't matter how they get all of this permission, but we didn't thought about this site to be a real ASR system in the past. And we start to give permissions to people to pump the water, which is fine according to the regulations. But now we came back to this important area and we found that no, without stopping all the operations around and with the existence of the dam, this aquifer, which is one of the strategic aquifer system for us, for the water supply, is not a good candidate for the ASR site because of our interference and development in the site in the last few years. And this is my message here. And at the end, I would like to acknowledge, and here I'm just saying visible and invisible side. So visible, but we make it invisible, and it should be the opposite, invisible, and we have to make it visible. So this is where also our interference becoming very bad in terms of water supply and water resources. At the end, I would like to acknowledge the whole team. This work is a work of, I guess, about 2 to 3 years. And where ESD and ACWUA, Acacia, and Nama Water contributed to all the work. So I think, in my opinion, because I was part of this whole project, this is itself requires a full 2 sessions to present the learning experience we get from this. And this is very important because all the Gulf countries now heading to ASR. Some countries, they are planning for it, they are in the tendering, and others are putting the terms of reference and the scope of work. I think it's very important to learn from each other's experience. Thank you very much for being patient with me. Thank you.
So, Dr. Ali, thank you very much for this nice presentation, and also for the investigation sites for the artificial research, very important in order to promote the groundwater management. So we will leave, sure we will have some discussion later on this, on your work and your activities on this artificial research, because it's very important as a solution for groundwater management. So now we will skip to the next presentation, which will be done by Ali Al-Hamdi on civil society participation in constructing small storage dams, the experience of the Sultanate of Oman, and you have 15 minutes, please, to present the main result of your participation of the society. Thank you.
Thank you.
مهندس علي الحامدي، مؤسس ورئيس مجلس إدارة أزر للهندسة والاستثمار القابضة، نائب رئيس المؤسسة الوقفية العامة بصحار سابقاً، عضو بمجلس إدارة شركة صلالة لخدمات الصرف الصحي، جهاز الاستثمار العماني مجموعة نماء القابضة سابقاً، عضو مجلس إدارة جمعية علوم وتقنية المياه الخليجية بمملكة البحرين، عضو مجلس إدارة الجمعية العمانية للمياه، ممثل الجمعية العمانية للمياه في إعداد رؤية عمان 2040 وفي إعداد استراتيجية عمان للتعدين في عام 2018، وهو عضو مشارك في الجمعية العمانية للمياه بالمنظمة العربية للثقافة والعلوم. مؤهلات العلمية والخبرة، حاصل على درجة البكالوريوس من تخصص الجيولوجيا جامعة سلطان قابوس 93، وأيضا لديه ماجستير في الإدارة العامة من الكلية الحديثة للتجارة والعلوم محافظة مسقط، وهو طالب دكتوراه بجامعة صفاقس بالجمهورية التونسية. وعنوان الأطروحة هو حول موضوع الأثر الاقتصادي لفاقد المياه في الشبكات العامة بسلطنة عمان، ولديه خبرة 20 عاما في المجال الحكومي إدارة الموارد المائية، و15 عاما في تأسيس وقيادة العمل الحر.
شكرا. بسم الله الرحمن الرحيم. أنا ما بأخذ إن شاء الله من الوقت الكثير، لأنه أيضا عندي موعد المغادرة بعد شوي. أتحدث اليوم حول تجربة في إشراك المجتمع المدني في إنشاء السدود التخزينية الصغيرة. طبعا يعني احنا بداية المحاضرة أطرح هذا السؤال: هل يمكن إشراك المجتمع المدني ممثلا في الأفراد أو الجماعات أو المؤسسات في إنشاء وإدارة وتشغيل السدود التخزين السطحي؟ هذه تجربة اعتبرها أنها تجربة فريدة انطلقت في سلطنة عمان نتيجة طبعا للظروف الجغرافية، حيث أن السلطنة مثل ما نعرف كلنا أنها تقع في حزام الجاف وشبه الجاف، ومعدلات الهطول المطري فيها لا تتجاوز 79 ملم في السنة، وبالتالي تعاني مثل غيرها من الجفاف خصوصا في الحزام الجبلي. كانت هناك مطالبات كثيرة من الأهالي بالضغط على الوزارة لإنشاء السدود التخزينية، لكن السدود طبعا تكلف موارد مالية كبيرة إضافة إلى موضوع التشغيل والصيانة. فبدأت المطالبات بأن يسمح للأهالي بأن يقوموا بأنفسهم بتمويل هذه السدود وإدارتها وتشغيلها وصيانتها. نتيجة لهذا الضغط بدأت الوزارة طبعا استجابت لها وبدأت في السماح للأهالي بالقيام بهذا الدور، ولذلك أحببت أن أسلط الضوء حول هذا الموضوع الذي أعتقد أنه بغاية من الأهمية، لأنه إنشاء السدود هو عمل علمي متقن، وأيضا لابد أن تقوم به مؤسسات حكومية، إضافة إلى كون هذه السدود فيها من المخاطر الشيء الكثير. لكن هل يمكن إسناد جزء من هذا العمل إلى المجتمع المدني فيقوم هو بعملية الإنشاء والإدارة والتشغيل؟ محتوى الورقة سيكون حول إحصائية عن أنواع السدود في السلطنة، التعريف بهذه المبادرة، الإجراءات الخاصة التي قامت بها الحكومة من أجل السماح للمجتمع المدني بالقيام بمثل هذه المشاريع، إحصائية عن مشاريع السدود المنفذة من بداية المبادرة حتى اليوم، وإحصائية أيضا عن سدود قيد الإنشاء. ثم أيضا نستعرض في نهاية الورقة قبل التوصيات مقطع فيديو لأحد الأودية الذي يحوي مثل هذه السدود بشكل متوالي، عبارة عن 6 سدود متتالية، بما يشكل بعد هطول الأمطار الأخيرة كأنه نهر جاري. السدود في سلطنة عمان حسب إحصائيات 2023 مجموعها 187 سد، طبعا بسعة تخزينية تصل إلى 357,949 مليون متر مكعب، منها 67 سدود تغذية جوفية، و115 سدود تخزين سطحي، و5 سدود للحماية من مخاطر الفيضانات. نأتي الآن إلى هذه بالنسبة للسدود التي قامت بها الحكومة إشراف وتشغيل وصيانة. نأتي الآن إلى التعريف بهذه المبادرة. نتيجة للضغط طبعا أغلب هذه السدود تم تنفيذها في الأحباس العليا للأودية والمستجمعات المائية، نظرا لأن هذه القرى تعاني من شح كبير من المياه خصوصا في فترة الصيف. هناك جهود لإيصال المياه للشرب وتمت، لكن بقيت المشكلة الرئيسية في الحصول على المياه لتغطية الإنتاج الزراعي. نتيجة لهذه الضغوط بدأ العمل في عام 2017، تم فتح المجال للمشاركة في تمويل وإدارة وتشغيل إقامة هذه السدود، والتي بلغت حتى اليوم 38 سد متوزعة في 3 محافظات من محافظات السلطنة. تبلغ القيمة الإجمالية لإنشاء هذه السدود 2,559,183 ريال عماني، أي ما يعادل 6,734,692 دولار أمريكي، وبسعات تخزينية تقدر ب4,294,000 متر مكعب سنوياً من مياه الأمطار. قامت الوزارة من أجل اللي هي وزارة الثروة الزراعية حالياً، وزارة الثروة الزراعية والسمكية وموارد المياه، من أجل ضبط هذه العملية، وأيضاً حتى يعني تتفادى الكثير من المخاطر في الولوج في مثل هذه المشاريع. قامت بمجموعة كبيرة من الإجراءات. بدأت تستقبل هذه الطلبات، ولا بد طبعاً أن تكون مقدمة من الأهالي، وعندهم 2 مفوضين بالتوقيع، تعتمد من الجهات الرسمية وتقدم إلى الوزارة. تبدأ الوزارة بعد ذلك بدراسة هذه الطلبات، ويتم من خلال هذه الدراسة تحديد الموقع الذي سيقام فيه السد، بما يخدم ويعزز مصادر المياه الموجودة في تلك القرى. تقوم الوزارة أيضاً بمساعدة منها بإعداد الرسومات والتصاميم والدور الإشرافي لتنفيذ هذا المشروع، ويقتصر دور الأهالي في هذا المشروع على التمويل، جمع الأموال اللازمة لهذا المشروع، والتعاقد أيضا مع مقاول التنفيذ. تم السماح أيضا من الجانب الاجتماعي للمفوضين بالتوقيع بالحراك الإعلامي من أجل الترويج لهذا المشروع الخيري، ولذلك يسمح لهم عبر وسائل التواصل الاجتماعي أن يقوموا بجمع هذه المبالغ في الحساب المخصص لهذا المشروع. وطبعا الحساب البنكي أيضا هناك يعني تدقيق على هذا الحساب، فلا يتم الصرف منه أو إدخال مبالغ إليه إلا بإشراف المختصين من الوزارة ولهذا المشروع تحديدا. بعد انتهاء طبعا تقوم الوزارة أيضا في ذات الوقت أو تتعهد بصيانة هذا المشروع بعد الانتهاء من تنفيذه. يبقى الدور المقتصر على الأهالي أو على المجتمع المدني في تجميع المال اللازم، في التعاقد مع المقاول، في متابعة إنشاء هذا المشروع، في صيانته وفي تشغيله وفي الاستفادة منه. أيضا قامت الوزارة يعني بإعطاء منحة مالية تقدر ب20% من تكلفة هذا المشروع، وال8% يتحملها الأهالي. هذه السدود طبعا تقيد من ضمن سجلات السدود لدى الوزارة وتتم متابعتها دوريا. هذه إحصائية للسدود المنفذة من بداية المبادرة حتى اليوم. طبعا هذه السدود تم الانتهاء منها، وهي في 3 محافظات، في محافظة الظاهرة والداخلية وشمال الباطنة. مجموع تكلفة المشروع لهذه عدد 19 سد، هذه اللي تم الانتهاء منها 1,704,183 ريال. ساهمت فيها الوزارة، أو الدعم المقدم من الجهة الحكومية هو 281,136. هذه صورة لأحد السدود في ولاية سمائل بمحافظة الداخلية، سد وادي محرم. وهذا أيضا سد قيد الإنشاء، سد وادي الجب بولاية انقل بمحافظة الظاهرة. هذا أيضا سد آخر في ولاية صحن بمحافظة شمال الباطنة. أما السدود قيد الإنشاء فيبلغ عددها 19 سد، بتكلفة إجمالية 855,000 ريال عماني، وتتراوح ارتفاعها ما بين 5 إلى 13 متر، وبأطوال من 24 إلى 244 متر، وبسعات تخزينية تتراوح بين 5,000 إلى 80,000 متر مكعب، وبمتوسط تخزيني يصل إلى 807,500 متر مكعب من مياه الأمطار. هذه طبعا السدود البقية اللي تكمل العدد الإجمالي لهذه السدود 38 سد. عذرا يمكن شوي، لا خلاص بس أريد استعرض الفيلم. أيوة. لا لا. هذا مقطع طبعا تم تصويره عن طريق طائرة الدرون لعدد 6 سدود تخزينية متتالية في أحد الأودية الرئيسية بمحافظة الظاهرة. ما يشتغل. مثل ما نلاحظ السدود ال6 متتالية في هذا الوادي الرئيسي، وكلها ممتلئة بالمياه من بعد المنخفض اللي صار في شهر مارس. نأتي الآن إلى التوصيات. هذه طبعا تجربة وليدة بدأت من 2013 لحد اليوم، يعني ولا زالت هي جهود قائمة ما بين الأهالي وما بين الوزارة في أخذ التصاريح والقيام بهذه المشاريع. وصل عددها إلى 38. أرى من الضرورة إسهام المؤسسات الأكاديمية المتخصصة في قضايا المياه المختلفة في دراسة التأثيرات الإيجابية لهذه السدود أو لهذه التجربة في تعزيز المخزون الجوفي وتعزيز مصادر المياه في المواقع التي يتم إنشاء هذه السدود فيها. نقطة الأخرى أيضا زيادة نسبة المساهمة المجتمعية في توفير الأموال اللازمة لإنشاء هذه السدود من خلال اعتبارها رسميا من جنس العمل الخيري المستدام وتشجيع الأفراد والمؤسسات لدعمها ماليا. قيام الجمعيات المهنية كجمعية علوم وتقنية المياه الخليجية والعمانية للمياه بتبني هذه المشروعات والإعداد لصندوق تمويلي خاص بها محليا وخليجيا. تسهيل الإجراءات الكفيلة باعتبار هذه السدود مزار سياحي وتشجيع الاستثمار فيها. الاهتمام بالإنتاج الزراعي في القرى التي تغذيها هذه السدود إنتاجا وحصادا وتسويقا وتصنيعا إن أمكن. إيجاد بدائل أخرى في عمليات إنشاء هذا النوع من السدود بما يسرع من عملية الإنشاء ويمكن من القيام بعمليات التنظيف الدوري لتلك السدود والاستفادة من الطمي المتراكم فيها في تخصيب تربة القرى المحيطة. ربط مواقع إنشاء تلك السدود جغرافيا بالمستجمعات المائية التي تنتمي إليها حتى يسهل دراسة تأثيراتها الإيجابية على تدفق المياه السطحية المستدامة وعلى تعزيز المخزون الجوفي. استبدال طلبات إنشاء آبار مساعدة للأفلاج لأنها تسحب المياه إلا التعرض للجفاف بإنشاء سدود تخزين سطحي لها. وشكرا.
شكرا علي الحامدي على هذه المداخلة القيمة، خصوصا حول هذه التجربة الرائدة في سلطنة عمان. وممكن نناقش كثير حول هذه المشاركة لأنها طبعا مشاركة قيمة، وربما في منطقتنا العربية رائدة، لأن مشاركة المجتمع المدني في إنشاء السدود هذا مهم جدا. بس ما هي هناك كثير من الكونسترينت، وهناك كثير من اللي ممكن نتوقعها لما نشرع في إنشاء سدود مثل هذه، لأن فيها تمويل وإلى غير ذلك. فلما يكون تمويل دائما الدولة تحتاط كثيرا في التمويلات. على كل حال هي تجربة رائدة، وممكن إن شاء الله ناخذ بهذه النتائج هذه المشاركة في إنشاء السدود التخزينية. وتوصيات كلها كانت كويسة، التوصيات حول تجربتكم الرائدة. فشكرا على هذه المداخلة. الآن نمر إلى آخر مداخلة في هذه الفترة المسائية، فنمر to the next presentation on groundwater aquifer susceptibility index of waterborne disease outbreak in the Nile Delta in Egypt, and it will be done by Muhandis Karim Suleiman. Can you please give?
Yeah. Engineer Karim Suleiman is a hydrogeologist. He has 2 master's degrees, one from Cairo and the other one is from Germany. And he has some experience in different hydrogeological calculations and variables and designing of a flash flood protections. Yes.
Just to inform you that it will be. Okay, so it will be online presentation. And مهندس كريم أنت معنا؟
نعم أنا معك.
Okay.
أنا موجود.
So you have the floor is yours, and you can make your presentation, please. And you have 15 minutes, please. Thank you.
Actually, I cannot share my screen. I have a technical problem here. I cannot share my screen. the host has disabled participant from screen sharing.
No, it will come. The organizer said me that it will appear immediately. So please, you can continue because it will be operated from the organizers.
Okay. Okay. Good afternoon, everybody. First of all, before we start, I would like to mention that I am going to present this presentation on behalf of Dr. Osama Salam as a co-author. And secondly, unfortunately, we didn't get the chance to come to Doha to present our work due to certain circumstances. And finally, I would like to thank the committee members of Gulf Water Conference who gave us the opportunity to present our work in its 15th edition. So we are going to present our work titled Groundwater Aquifers Susceptibility Index of Waterborne Diseases Outbreaks, and our case study is located in Nile Delta, Egypt. So here is our agenda for our today's presentation. So firstly, I will explain what the problem is and mention the objectives of this study. And then I will describe the study area, show the adopted methodology for this study, and then I will show the results, and we will end by conclusion and recommendations part. So what is the problem actually? So actually sewage water is considered as the primary source of microbiological contamination of groundwater. And this sewage water, as you know, contains a group of pathogens such as bacteria, viruses, protozoa, etc. And due to poor sanitation conditions of urban areas and settlements, this might lead to a major waterborne diseases and could spread waterborne diseases through groundwater. And of course, it could evolve a disease hotspots. And actually, we could adopt a tool such as wastewater monitoring to trace the different waterborne diseases such as SARS, and the tools might be developed to detect the areas vulnerable to waterborne diseases through groundwater. Here, as you could see in this figure, you will find this figure shows the degree of risk of spread of waterborne diseases in Egypt. And as you could see here, you will find that most governorates or most Egyptian governorates has a high risk of outbreak of the waterborne diseases. So most of governorates are exceeding, their risk are exceeding 50%. And of course, the spread of these diseases comes from the transmission through the sewage water, through groundwater, and then this causes some sort of outbreak of certain food and waterborne diseases. So our main objective here is to develop an index for evaluating groundwater aquifers susceptibility waterborne diseases. And through this main objectives, we have we have actually accomplished some objectives through developing a methodology for this index, applying this method on Nile Delta region, validate the parameters that are used to calculate the aquifer susceptibility index, and finally we classify the study area through a spatial distribution of this index. So here's our study area, the Nile Delta. So it's located in the northern part of Egypt, and it consists of the following governorates: Qalyubiyya, Munufiyya, Sharqiyya, Gharbiya, Buhaira, Alexandria, Kafr al-Sheikh, Daqahliya, and Damyat. So here is our methodology. So firstly, we have collected the parameters related to calculating the index, and we have actually created thematic layers for these parameters. And the parameters actually includes the groundwater hydrogeological parameters and anthropogenic parameters. And then we have specified the weighting for these parameters through diaristic weighting for hydrogeological parameters and aquifer susceptibility index for the water-borne diseases for the anthropogenic parameters. And then we specified the range and the rating of these parameters. And then we calculate the index of aquifer susceptibility through weighted linear combination method. And finally, we conducted a sensitivity analysis to determine which parameter has the highest significant impact on the index or on the results of the index. Here I would like to show you the thematic layers of the parameters that we have actually chosen, or we have actually chosen for this study. So I will start with hydrogeological parameters. So firstly, the depth to water, and as you could see here in the left figure, that the depth to groundwater ranges from 0 below surface layer to around 30 meters. And the second parameter was the recharge rate, and it varies from lower than 50 millimeter per year to around 300 millimeter per year. And the third parameter was the aquifer media, and we have actually classified the aquifer media based on the soil texture of the aquifer matrix. And finally, we used the hydraulic conductivity parameter in our analysis, and it ranges from around 28 meter per day in the north, and it increases if we go towards the southern part of the study area until it reaches to more than 82 meter per day. Now we will turn to the anthropogenic parameters. So the first parameter was the sewage network system. So the green colors represent, or the green areas represent the areas which are covered by wastewater network system. Second parameter was drains density, and the red areas indicate that these areas are has high density, high drains density, and vice versa. And then we have included the urbanization of the cities in our study. And of course, there is a direct relationship between the urbanization and the outbreak of the diseases. waterborne diseases. And finally, we have included the population density, and the red color indicates that these areas are highly populated. So after we have conducted the calculation of the index through assigning the weighting for each parameter and specifying the range of the classifications, we got a spatial mapping of the aquifer suspectability index waterborne disease for the study area. And as we could observe, we can find that the southern part of the study area are highly vulnerable to the spread of waterborne diseases, and especially at Qalubayya Governorate, Munafaya, and Gharbeya Governorate. On the other hand, the northern part of the Nile Delta is expecting low vulnerability to spread of waterborne diseases, especially at Kafr Sheikh Governorate and the northern part of Bahira Governorate. Here is a bar plot showing the classification of the aquifer susceptibility index for each governorate, and we could observe that Qalubayya has the highest risk to the outspread to the waterborne diseases, and the second governorate was Munafaya, and the last governorate was, or the third governorate was Gharbeya, and Kafr Sheikh has the lowest risk to the outbreak of the waterborne diseases. Here are the results of the sensitivity analysis. We have actually conducted sensitivity analysis to determine which parameter has the highest impact on the results of the index. And we could find that most of the, or all of the anthropogenic parameters are actually sensitive, or the results are very sensitive to these parameters. And regarding the hydrogeological parameters, we'll find that the aquifer media and tips to the groundwater are has a higher impact on the results. So to conclude, so first of all, we found that the aquifer susceptibility index has proved that we could include the anthropogenic parameters to determine the susceptibility to waterborne diseases. And of course, this framework could be applied in other regions, but of course, we have to take into consideration the adjustment of the weighting factors, and this should be based on site conditions. And it's recommended to improve the irrigation system and prevent the continuous drainage of the sewage and wastewater to canals. And of course, we have to actually implement new wastewater treatment plant so that we could reduce the transmission of waterborne diseases to, or the outbreak of the waterborne diseases. Sewage treatment services must be developed, especially at Qalubayya, Gharbeya, and Munafaya as a high priority. So this governorate should have the high priority. And finally, I would end that public awareness is very, very important to be implemented at this, especially at these vulnerable areas. So thank you for your attention, and I would be grateful to answer any questions from your side.
So thank you very much, Muhandis Karim. for this excellent presentation on the susceptibility index in the Nile Delta in Egypt. So we got a very nice susceptibility index map, which is based on several parameters elaborated under thematic maps. This is exactly, and you have analyzed, and it is the result is very important for the groundwater management in this Nile Delta. So please stay connected with us for discussion. And now I can open 5 minutes. Okay, so we have 5 minutes of discussion. Please, I can give probably the floor to 2 or 3 questions. Okay? So, please.
محمد الصوفي سعودي أرابيا. الأخوة في عمان الاثنين، واحد فيهم اشتغل على الريتشارج والثاني اشتغل على السدود. اللي اشتغل على الريتشارج احنا تجربتنا في السعودية we don't have surplus water in winter or summer. Why? Because we schedule our maintenance and overhaul and shutdowns all in winter. So that way, we don't have surplus and we didn't need to do a recharge. Asar and Dasar is out of Saudi Arabia, as far as I can understand. The question we have for other gentleman, but he left, he said 20% is donation from the government. But it's actually 20%, maybe it's 50%, because the design, the supervision, the site selection, all done by the government. So there's a contribution of government of about 50%. I think there was another question here around here, which is how do you recover the cost? It didn't mention there. نسأل بعدين. مع السلامة.
Why do you have surplus? Why don't you schedule your maintenance?
Okay. Dr. Ali, the question is for you.
So, what maintenance we have to schedule here? I don't get the question properly. The excess water we get is from desalination production, based on a contract patterns. So during winter time, there is a low peak demand. Well, this is something I don't want to discuss here, but there is a surplus here, and I'm quite sure also this is in several countries. I don't know about Saudi Arabia, but the situation in most of the Gulf countries, there is a surplus. And that's why, this is the situation here. We don't map it to what is happening in Saudi Arabia. What is happening in Oman, there is a surplus during winter time. And I think the same situation in UAE. So UAE, they have an ASR system which is in place also. And this is where they are injecting excess desalinated water to be used later on.
زين سؤال بس آخر سؤال إذا سمحت لي. أنا ويا أخوك المهندس عادل الصيص. جدا والله فكرة رائدة نفس ما قال إن المجتمع المدني يشارك الحكومة في صناعة السدود. لكن أنا شدني منظر السدود وهم نازلين يعني ليش ما استخدمت لإنتاج الطاقة الكهربائية؟ أنا كنت حاب أسأل السؤال هذا أيوه. يعني لو حق الغرب بسيط.
مش موجود.
توصل له.
هو اعتذر لأنه عنده التزام.
فكرة قابلة للتطبيق.
ممكن دكتور علي.
بس. انا ممكن اقول طبعا ديت يعني دي فلاش بلس بتيجي مش سستينبل، يعني مش موجوده على طول. يعني لو هو اعتمد على الجنريشن بتاع الكهرباء مش هتبقى موجوده. يعني ممكن لو جت في مره كل سنه تبقى خير، يعني فهتبقى موجوده قد ايه؟ يعني اسبوعين 3، فالانتاج مش هيبقى يعني عملي على ما اظن. يمكن هم يكون عندهم حاجه زي كده او غير يعني. لكن
لا هو انتاج طاقه لازم اوكي question please.
السلام عليكم.
My questions to
Dr. Ali Al-Maktoumi. ASR project needs to consider environmental impacts. Can you discuss the potential environmental concern associated with ASR in the Oman case study, such as hydrogeochemical changes or induced seismic activities? Does the study propose any monitoring strategies to mitigate this potential risk and ensure the long-term sustainability of the ASR?
If I get your question correct, you are talking about deterioration of the water quality after injection, or?
Yeah, about environmental impacts, environmental concern.
Well, the work I presented here is not a long-term storage. In fact, here, as I mentioned, the horizon in terms of time is 1 year cycle. So we are injecting for 4 years because we have evidences and data of the surplus during certain period of time, and that water has to be injected during the low peak demand and then stay in rest in the aquifer for about 38 weeks and then recover during summer, where we are putting more pressure on the desalination during high peak time. So during that year, according to the preliminary hydrochemistry and geochemistry studies, there is no actual impact. The time is very limited. However, each site here will undergo a piloting project, and will start soon with one of the sites. Not the one I'm presenting, it's out of question because of the hydrologically and technically becomes invisible because of the shift or the drift of the injected bubbles. But for other sites, we will start with this long term of residency and to have a dense analysis of the chemistry from the site. But this is in place for in the plan, in the piloting project, which has to be soon.
Okay. So thank you. I am sorry because there is a workshop, so we have to stop. By this, I would like to thank all كل المتحدثين وكذلك المشاركين، كل المشاركين هنا على هذا الفترة المسائية.
Thank you. Now we have the workshop. Rola, can you come with your team, please? I have some announcement. Tomorrow, after the conclusion and recommendation session, we will be distributing the certificates for the participation, and then we will have a group picture for all the participants, okay?